hypothesis testing in our regressions, and how heteroskedasticity will change that. We'll do a lot of hypothesis testing on one or several regression coefficients. There's an important distinction between doing a t-test on an individual regression coefficient versus doing an f-test on a set of regression coefficients taken together, sometimes all the slope coefficients. In the univariate regression, the t-test on significance gives the same p-value as the f-test for whether all the x variables jointly are different from 0, because in a univariate regression, all of them is the same as one of them. There's only one. But with multivariate regression, the f-test is testing on whether all the slope coefficients are, each and every one of them, 0. Remember from the univariate case, a zero slope of a regression just says there's no relationship between x and y. Y varies up and down, x varies left and right, but there's no particular relationship there. That would be a zero slope. In the multidimensional case, with lots of x variables, the zero slope generalizes there. Often we want to form tests about whether a group of beta coefficients are all equal to 0. And that's different than testing if they're one at a time different from 0. For instance, if we have a bunch of dummy variables for education, we might want to test whether education overall is useful in prediction. That can be done with a linear hypothesis package in R. Let's step back a bit and think how these tests are generally set up. We measure the accuracy of a model with a sum of squared errors. Remember back when we introduced ordinary least squares and explained the procedure was to minimize the squared errors, make the squares least. Each error is y minus predicted value, which is based on the model, squared. The model coefficients are chosen to make those squared errors as small as possible. An accurate model has a smaller sum of squared errors. If I add one or more x variables, then the error is certainly not going to increase. At worst, those new x variables might be totally useless. But in general, even if they're random numbers, they might improve things a little bit. Which is actually a bit of a problem, since a rule of add x as long as it reduces the sum of squared errors would be no good. Instead, I have to ask a bit more sophisticated question. Did the sum of squared errors go down by a lot? Is that a big reduction in the sum of squared errors? This goes back to what McCloskey identified as the classic statistics problem. How big is big? Is there a big difference in the sum of squared errors between two models where one has more x variables? Or, as an economist might put it, if adding more x variables has a marginal cost, then how large is the marginal benefit? Rational decision-making has to make a trade-off and compare marginal benefit with marginal cost. Adding x variables makes the error smaller. Dropping x variables makes the error bigger. What's the best choice? Adding a set of variables and asking about their marginal benefit in the model is often done in the case where I have a set of dummy variables, such as a set of education dummies. As a final note, as I've reminded you before, statistical significance is not identical to importance. It's quite possible things could be important even if they're not statistically significant, or vice versa. They may be statistically significant, but unimportant. We have lots of nice mathematics about statistical significance, but not nearly so much about actual importance. That takes your judgment. Looking a bit deeper at the formulas, the sum of squared errors, sometimes called sum of squared residuals, is the sum of each error term, squared. Each error term is y minus the beta hat value times x. When we compare two models, we typically assume one is nested within the other. It's a proper subset with fewer x variables, not different x variables. The sum of squared residuals, SSR, for the base model with fewer variables is SSR naught. Then the model with more x variables gives SSR 1. Therefore, SSR naught must be larger. Fewer variables means larger errors. We then find the percent change in the sum of squared residuals, so that is, in some sense, the benefit from adding more x variables. But note the squiggly equal sign. This is an approximation for now. To make it better, we'd want something more like an elasticity than just a percent change. We want to take the percent change in the sum of squared residuals and divide that by this percent change in the number of x variables. In this notation, the base model has k x variables, while model 1 has k plus q x variables. Model 0 has n minus k minus 1 degrees of freedom. Model 1 has q more variables and therefore q fewer degrees of freedom. That means the percent change in degrees of freedom, that's given there. Divide the percent change in sum of squared errors by the percent change in number of x variables. That gives us the F statistic. That formula is complicated enough. It's only exact if we have homoscedastic errors. In the presence of heteroscedasticity, that formula is going to get even uglier. So we let the computer do the calculations. But it's useful to keep in mind the basic insight that this complicated formula is at base kind of like what we did back in Principles of Microeconomics, finding an elasticity. I mentioned heteroscedasticity, which is a big word. It's extraordinarily common. It means that in a regression line, the errors get spread wider or narrower depending on some x variables. The classic case is looking at people's wages as they get older. They tend to spread farther out as they get older. Recent college grads tend to get a pretty narrow range of offers, conditional on major, but then their wages spread out over the span of their career. Some people get on a fast track, others might not. We see that as heteroscedasticity. There's a wider spread of wages among people with a higher age. In a Stock and Watson textbook, they always use heteroscedasticity consistent standard errors. Sometimes you'll see these referred to as Eicher, Huber, White errors. Well, those are the three authors who did work developing them. Sometimes you only see 2 out of 3 or 1 out of 3. As you read econometric studies, you might also see HAC standard errors, heteroscedasticity and autocorrelation consistent, sometimes called Newey West for those authors. That's more common in time series. The formulas are ugly, require some notation from linear algebra, but have R do the difficult work and use the COIF test to use the heteroscedasticity consistent standard errors. That does not change the coefficient estimates, only changes the standard errors. Although in turn that does change the t-stats and the p-values that are calculated. Usually the standard errors get larger, which means t-stat goes down and the p-value goes up. So estimates that looked statistically significant might become insignificant with the correction.